What 3i Atlas is doing right now shouldn't be possible, and yet here we are. In this video we're diving into how 3i Atlas just became suddenly 16 times brighter, an explosive jump that defies what astronomers expected from an interstellar visitor. We'll unpack what that brightness surge really means, hint it's roughly a 3 magnitude leap, explore the physics that could cause it, and ask the big question: is 3i Atlas breaking the rules, or teaching us new ones? By the end, you'll know exactly why this moment matters, and what to watch for next. Before we get into why it was suddenly 16 times brighter, it helps to meet the traveller at the centre of the story, 3i Atlas. The name sounds whimsical, but it's really just astronomer shorthand. The 3 marks it as the third object ever confirmed to have come from outside our solar system, after the famous Oumuamua and Borisov. The I stands for interstellar, and Atlas is the sky survey project that first spotted it, a network built to sweep the heavens every clear night and catch anything new that moves. In other words, third interstellar visitor, discovered by ATLAS. Simple name, extraordinary origin. Atlas itself is worth a quick detour because it explains why 3i Atlas didn't slip past unnoticed. The project runs small, fast robotic telescopes spread across both hemispheres, 2 in Hawaii and others in Chile and South Africa, that scan the entire visible sky multiple times per night. By taking frequent wide-field images and comparing them, the system flags faint specks that change position from one exposure to the next. Most of those specks are routine near-Earth asteroids, but on a night in early July 2025, one of those moving points had a telltale trajectory. It wasn't looping around the sun like a local, it was barreling through on a one-and-done flyby. That's how the alert for 3i Atlas was raised, and within hours observatories worldwide began to follow up. What makes 3i Atlas interstellar isn't a label, it's its path through space. Local comets travel on closed, elongated loops. Given enough time, they return. This object doesn't. Its track is open and unbound. It swoops in from the deep, swings around the sun, and then heads back out forever. You can picture it like a stone skipping past a campfire, close enough to heat up but never captured by the flames. That open road through the solar system is the smoking gun that it started life around some other star and wandered for ages before drifting into our neighbourhood. Because of that fast freewheeling path, timing matters. 3i Atlas reached its closest approach to the Sun around the end of October 2025, not especially close by comet standards, roughly 1.5 times Earth's distance from the Sun, yet close enough to wake up its ices and paint a faint tail. The moment it warmed, the object announced itself not just as a rock but as a comet, streaming gas and dust that telescopes could catch. Even though it was never destined to become a dazzling naked-eye spectacle, that activity gave scientists exactly what they needed: material to analyse, light to measure, and a rare chance to compare alien comet stuff with the comets we know. One charming part of this story is how many eyes turn toward the same visitor. On Earth, big observatories chased it whenever it cleared the horizon. In space, Hubble snapped crisp images that help refine its size and activity, while NASA's James Webb Space Telescope grabbed infrared spectra, essentially chemical fingerprints, of the gas streaming off it. ESA even coordinated observations from missions at Mars and around Jupiter to watch it from different vantage points while it hid in the sun's glare from our point of view. For a single, faint speck, 3i Atlas had quite the paparazzi. So what are we learning from this quiet comet with the loud name? First, that interstellar comet isn't a contradiction. Oumuamua teased us with strange behaviour but no obvious comet tail. Borisov behaved more like the classic icy wanderers we're used to. 3i Atlas sits in that lineage but brings its own quirks. Subtle differences in how it brightens, what gases it vents, and how dust streams away under sunlight. Each of those details helps scientists test ideas about how comets form around other stars, how they're tossed into interstellar space, and what happens to them after millions of years drifting between suns. In a sense, the object is a sample return mission that the galaxy did for us, a messenger from elsewhere, delivering its chemistry right to our instruments. It also reminds us how much modern sky surveys have changed the game. 20 years ago, an object like this could have slipped by unannounced. Today, purpose-built systems like Atlas cast a wide, fast net. When something unusual shows up, a global relay snaps into action. Within days of discovery, 3i Atlas had a preliminary orbit, observing plans and a calendar of when to watch as it headed toward and then past the sun. That choreography, small scopes finding, big scopes dissecting, space telescopes confirming, is how a blurry dot turns into a story about another solar system's leftovers. For the rest of us, 3i Atlas is a reality check on scale and time. It left a home we'll never see up close. It crossed the void for ages, probably battered by cosmic rays and micrometeorites, its surface baked into a crust until sunlight from our star cracked it open again. For a few months in 2025 it threaded the inner solar system, faint but consequential, and then slipped away. No return ticket, no second chance. You couldn't walk outside and gaze at it with the naked eye, but in that faint fuzz, in those spectra and light curves, was a universe of context. How common these visitors might be, how their ices compare to ours, how planetary systems everywhere shed icy crumbs into the dark. And that brings us back to the shocker, the shouldn't be possible part of the title. When an interstellar visitor brightens in a surprising way, it isn't just a pretty light show. It's a clue that the physics and chemistry of its surface are doing something we didn't predict. Now that you've met 3i Atlas, the who, the what, and the why it matters, you're ready to appreciate what a sudden jump in brightness actually tells us about an object born under another sun, and why this fleeting encounter is such a big deal for science. When people say this shouldn't be possible, they don't mean nature broke its own rules. They mean our expectations did. With interstellar visitors, the safe bet is always subtle. You expect a small, dark body that brightens slowly and predictably as sunlight warms it, then fades just as smoothly on the way out. You expect a surface that's been baked and battered by eons of deep space radiation, sealed under a crust that muffles any dramatic activity. You especially don't expect a quiet speck to crank itself up to be suddenly, unmistakably brighter. So bright that amateurs and professionals alike can see the jump in their data. That's the first reason the reaction to 3i Atlas is so strong. It violated the Be Boring script. The second reason is timing. The normal comet playbook says activity ramps up as an object nears the sun, following a gentle, almost rhythmic curve. In that script, what you see is not a jump but a glide. Gas gently evaporating from ices, dust lifting and forming a soft coma, the tail stretching out in the predictable push of sunlight. A sudden leap in brightness is like a firework going off during a slow violin solo. It implies something more violent than steady warming. Pressure building under a crust until it vents, a slab splitting to expose fresh ice, or multiple jets switching on at once and flooding space with bright sunlight scattering dust. Then there's the interstellar twist. Bodies that have wandered between stars for ages are expected to be stingy with their ices. Picture a traveller wearing a thick, dusty coat. Over time, the top layers get sintered, microscopically fused by radiation, until they become tough and less welcoming to heat. That kind of skin traps the volatiles beneath it, and it also insulates against fast dramatic changes. In other words, it's supposed to dampen fireworks, not stage them. So when 3I Atlas lights up, it hints that either the coat isn't as thick as we thought, or there's an unexpected reservoir of easily vaporized material hiding just under the surface. Both options tug at assumptions about what drifting for millions of years in interstellar space actually does to a small body. Another expectation that took a hit, the idea that brightness should be mostly about distance. Move closer to the sun, get brighter. Move away, get dimmer. Simple, right? But 3I Atlas is a reminder that geometry can be a magician. Fresh dust sprayed into space can act like a screen of tiny mirrors. Under the right angles, sunlight can be scattered forward, aimed toward us, making the comet appear far brighter than a distance-only model would predict. This isn't cheating, it's optics. Still, it shouldn't be possible if you're imagining the comet as a featureless dot. The moment you acknowledge plumes, grains, and viewing angles, brightness becomes a living, jumpy thing rather than a tidy curve. Rotation adds another layer of surprise. If 3I Atlas is spinning or even tumbling, jets act like little thrusters, changing which parts of the surface face the sun and for how long. A vent that was shadowed for weeks can suddenly face daylight for hours, pumping out gas and dust like a geyser. A lagging jet can switch on in a single rotation and flood the coma with new material. To an observer, that looks like a shouldn't-be-possible lurch from faint to vivid. But to the object itself, it's simply a matter of sunlight finally hitting the right patch of ice. There's also the question of what the object is made of. We're used to solar system comets that carry a familiar mix of water ice, carbon monoxide, carbon dioxide, organic gunk, and rock. Interstellar comets belong to other kitchens. If 3I Atlas carries a slightly different recipe, say, more of the supervolatile ices that boil off even when far from the sun, that could prime it for bigger, earlier, and more dramatic outbursts than we rehearsed for. It's not that the physics is new, it's that the ingredients are. When the pantry changes, so does the menu. Surface structure matters too. Think of a creme brulee, a hard shell with something reactive beneath. If the shell on 3I Atlas fractures because of thermal stress from day-night temperature swings, or because internal gas pressure finally wins, new pristine layers are exposed. Fresh ice sublimates far more vigorously than old crusted surfaces. That switch from sealed to fresh is like cracking a window in a stuffy house. Suddenly there's flow, and suddenly there's change. If the fracture propagates across a wider area, the effect multiplies. A brightness spike can be the visible signature of a domino line of tiny failures racing across the surface. All of this leads to an uncomfortable, wonderful truth. Our models are excellent at describing average behavior and terrible at predicting surprises. With 3I Atlas, the shouldn't be possible reaction reflects the gap between smooth classroom curves and the jagged reality of a fragile venting snowball. We simplify comets into elegant lines on a graph, but nature draws with splatters and smudges. Every outburst is a reminder that the inside of a small body is a maze of pores, layers, and seams. The difference between quiet and spectacular can be a few centimeters of crust, a slightly different spin rate, or a patch of grains that clump instead of flow. There's also the human factor. We're primed by the last two interstellar celebrities. Oumuamua was enigmatic. No obvious coma, but a peculiar push that stirred up debate. Borisov looked and behaved more like a classic comet, reassuringly textbook. When 3I Atlas shows a punchy brightness jump, it refuses to fit neatly into either box. It's not wrong. It's a third data point reminding us that interstellar is a category, not a clone stamp. The phrase "shouldn't be possible" is really shorthand for "wasn't on our bingo card" after just 2 examples. From a practical, observing standpoint, sudden brightening also messes with planning. Telescopes are scheduled, exposure times are calculated, surveys triage what to chase on a given night. A 16-fold leap can mean the difference between marginal data and rich detail. It can open the door to spectroscopy that was previously out of reach, or turn a target from maybe to must observe. When the sky surprises us like this, the scramble is real. That sense of whiplash, the way a faint curiosity turns into a headline target, is part of why people blurt out that it shouldn't happen. It's not that it can't, it's that we weren't ready. If you zoom out, the bigger story is philosophical. We like to believe that time smooths rough edges. An object that's been adrift between stars should be tame, worn down, predictable. 3i Atlas argues the opposite. Ancient doesn't mean quiet. Under the right light, with the right crack, even a veteran traveller can roar. The "shouldn't be possible" framing becomes a lesson in intellectual humility. Every new interstellar visitor widens the map of what small bodies can do. The rules aren't broken, they're broader than we imagined. And finally, there's the emotional truth. Part of the thrill of astronomy is that the universe still pulls stunts like this. You point a telescope at a visitor from another sun, expecting a gentle rise and fall, and it throws you a plot twist. That's not a failure of prediction. It's the cosmos keeping the story interesting. 3i Atlas is doing what comets do best, taking simple sunlight and turning it into drama. Whether the cause is a fresh vent, a lucky scattering angle, a change in spin, or a cocktail of all three, the surprise is the point. Shouldn't be possible is our way of saying, we've just been reminded there's more to learn. When people hear "suddenly 16 times brighter," it sounds like a headline trick. In astronomy, though, that phrase is a very specific kind of shock. Observers track brightness using a simple ladder of steps. Climb about 3 steps on that ladder, and you've effectively multiplied the light by roughly 16. For a quiet object like 3i Atlas, that's not just a glow-up. It's a declaration that something real and rapid changed in or around the comet. The telescope didn't magically get better. The sky didn't suddenly clear across the entire planet. The object itself started throwing a lot more sunlight back at us. So what does that actually look like? Imagine you've been taking nightly snapshots, each with careful, consistent settings. One night, the same exposure that used to reveal a modest fuzz now shows a larger, brighter, more textured halo. The comet's coma, that cloud of gas and dust around the nucleus, has ballooned and thickened. The core looks punchier. The tail stretches farther than your last frame could catch. If you're an amateur observer, it means shorter exposures suddenly work. If you're a professional, it means your spectrograph can now tease out faint fingerprints you couldn't see before. In both cases, the sky just handed you extra signal for free. Brightness for a comet is mostly about surface area and sunlight. A bare, small nucleus doesn't reflect much, but the moment it vents gas, it drags dust with it. Tiny grains that act like millions of little mirrors. Multiply the number of grains and you multiply the reflective area. Change the size of those grains and you change how efficiently they scatter light. Release especially fresh, clean ice dust, and you can bump the reflectivity again. That's why a sudden increase in dust production, the comet equivalent of turning on a fog machine, can boost brightness far beyond what distance alone would suggest. Geometry can add a spotlight effect. When the Sun, the comet and Earth line up just so, the dust in the coma can throw light forward toward us more strongly than in other configurations. It's the same reason fog looks blindingly bright in your car's headlights when you're driving straight into it, but much less dramatic from the side. If 3i Atlas happened to belch out a fresh sheet of fine dust, while the viewing angle favoured forward scattering, the apparent brightening would feel even more dramatic. Nothing about its intrinsic energy needs to change for that optical trick to play a role, just the angles and the grain properties. Of course, this isn't only about dust. Gas matters too, even if gas itself doesn't reflect as efficiently as solids. When activity spikes, gases like carbon monoxide, carbon dioxide and water vapour surge from cracks or vents. Some of that gas fluoresces in sunlight, adding faint colour-tinted contributions to the total light. More importantly, the gas is the engine that lifts dust off the surface. Think of it as the wind beneath the grains. A burst of gas flow can transform a sleepy coma into a luminous, expanding shell in a matter of hours. Why would 3i Atlas release so much so quickly? The most straightforward explanation is a fresh patch of ice suddenly exposed. A thin crust can seal in pressure like the top of a creme brulee. Thermal stress, a minor quake from shifting jets, or even the simple day-night cycle can crack that crust. Once it opens, trapped volatiles rush out and carry dust with them, and the comet's appearance changes fast. Another possibility is that the object's rotation brought a previously shadowed, volatile-rich region into full sunlight, switching on a jet that had been dormant. In time-lapse, it's like watching a lighthouse beam sweep across the sea, except the beam is a plume of material, and the sea is space. It's important to say what a 16-fold brightening doesn't mean. It doesn't mean the nucleus suddenly grew larger. It doesn't mean 3i Atlas jumped closer to Earth in a blink. It doesn't mean it turned into a star or started generating its own light. We're seeing more reflected sunlight because there's more stuff, more dust, better oriented dust, brighter dust, between us and the nucleus, and because the way that stuff interacts with light can change quickly. Think bigger disco ball, not new light bulb. Observers confirm that a jump is real by cross-checking everything that could fake it. They compare measurements from different telescopes, filters and locations. They verify that the reference stars in the image look normal, that the camera settings haven't changed, and that thin clouds didn't play a trick. When the reports agree, same increase, same timing, you can trust the sky. That's when the interpretation work begins. Is the coma expanding faster than before? Did the colour of the light shift, hinting at different dust sizes or gas contributions? Does the light vary on timescales that match a plausible rotation period? One of the most telling signatures after a surge is how the brightness decays. If the light drops back quickly, it suggests a brief geyser-like burst that vented and then quieted. If it plateaus at a new, higher level, maybe a large area of fresh ice remains exposed, feeding a sustained outflow. Sometimes brightness keeps climbing, but more gently, as the first eruption primes neighbouring regions to start contributing. Each pattern sketches a different portrait of the surface: cracked mosaic, single big vent, or cascading failure of a crust over a wider field. The texture of the coma tells a story too. In steady states, it can look smooth and symmetrical. After an outburst, it may show jets, fans, or subtle arcs, signs that material is leaving in preferred directions. These structures can shift from night to night as 3i Atlas rotates, giving astronomers clues about where the active regions sit on its surface and how the nucleus is oriented in space. Think of it as reading wind streaks in sand dunes to learn which way the gusts blow. For people following along from their backyard, a 16-fold pop is the difference between wondering if you're seeing anything at all and getting a clear, confident detection in modest gear. For science teams, it can be the difference between thin, noisy spectra and crisp measurements of specific molecules and dust features. That means better chemistry, better models, and better constraints on how interstellar comets are built. It's not just brighter, it's more informative. There's also a psychological shift that comes with a jump like this. Before, 3i Atlas might have been filed under Interesting Keep Tabs. After it moves to Urgent, Observe whenever possible. Schedulers reshuffle plans, observatories queue more time, collaborations spin up campaigns to cover multiple wavelengths at once, visible light for dust, infrared for warm grains and gas, radio for the coldest molecules. A single spike can turn a cautious story into a flood of data. In the end, suddenly 16 times brighter is less a mystery phrase and more a translation. Something on or around 3i Atlas changed quickly enough and strongly enough to throw far more sunlight our way. Whether that something is fresh ice exposed by a crack, a lucky alignment that makes dust behave like glitter, pointed straight at us, a new jet rotating into daylight, or a cocktail of all three, the meaning is the same. The comet just opened a window into its interior and its behaviour, and while the math behind the brightness scale stays tucked away, the takeaway is beautifully simple. More light means more story to tell. An outburst begins long before anyone notices it. For days or weeks, sunlight has been seeping into the surface of 3i Atlas, not just warming the skin, but sending a slow thermal wave a little deeper with every sunrise. Beneath the dusty crust lies a patchwork of ices and pores, tiny tunnels and cavities where gas can collect. Some of those ices are easy to wake, some need stronger light, and some carry a secret. When they rearrange their structure, they can release both trapped gases and a burst of extra heat. The result is a quietly loaded spring inside the comet, storing pressure and potential, waiting for a trigger. One trigger is the simplest: a crack. Day-night temperature swings make surfaces flex. Over time, hairline fractures explore the crust like roots. A small fissure links a gas-rich pocket to the surface, and the whole system changes state in an instant. What was trapped becomes free. What was sealed becomes a vent. Gas rushes through the new opening like air escaping a punctured tire, dragging dust with it. Because the gas is expanding into space, it accelerates quickly. Grains that were cemented in place are lifted, tumbled, and flung outward, forming a jet that looks thin and focused near the source, then feathers into a luminous fan. Another trigger starts even deeper. Some water ice can exist in a disordered, glassy form that loves to imprison other gases. Warm it enough, and it snaps into a more orderly state, kicking out those stowaway molecules and releasing heat as it transforms. That extra heat helps nearby ices vaporize faster, which raises the local pressure, which pries open more pathways, which releases more heat. A runaway loop that can turn a quiet patch into a geyser. No formulas are needed to grasp the effect. It's like kindling suddenly finding flame and sweeping through dry brush. Composition matters as much as mechanics. If a region is rich in the more eager ices that leap into gas at relatively low temperatures, it can awaken far from the sun. Imagine lifting the lid on a pot that's been steaming gently. The interior fog billows out, carrying droplets with it. In the comet's case, those droplets are microscopic dust grains and snowflakes. Freshly exposed, they're bright, clean surfaces that haven't had time to darken. A handful of square meters of new venting can feed a plume large enough to change how the entire comet looks in a telescope. Once the vent opens, the anatomy of the outburst unfolds in stages. First is ignition, the rapid rise in gas flow that strips loose material and scours the throat of the vent. Next comes plume formation. Dust becomes entrained, and the column of material fans along the direction away from the sun, shaped by sunlight and the comet's own motion. If 3i Atlas is rotating, the jet's base sweeps in a slow arc, tracing spirals and shells in the coma. Observers sometimes see these as faint layered arcs, like tree rings written in light, each one a snapshot of where the jet was pointing in a previous rotation. Grain size sets the mood. Very fine dust, smaller than a smoke particle, resists settling. It spreads into a smooth, bright haze that boosts the comet's total light dramatically. Slightly larger grains contribute texture, rays, stria, and fans that give the coma a ribbed look. Pebble-sized bits rarely travel far. They arc outward and then fall back in slow motion, a gentle rain that can blanket the source region and, ironically, begin to choke the vent that launched them. In that way, an outburst sows the seeds of its own end by building a fresh, insulating mantle. Inside the throat of the vent, the flow changes as the eruption matures. At first, pressure behind the opening is strong and steady. The gas stream stays coherent, like water from a well-pressured hose. As the reservoir empties or the vent widens, the flow softens. It can sputter if debris partially blocks the exit, then surge again when a clump breaks free. That sputter-surge pattern can translate into small flickers in brightness over minutes to hours. Zooming out, the coma continues to swell as yesterday's dust moves outward and today's dust replenishes the inner glow. Not every outburst comes from a pinhole vent. Sometimes a wall collapses. Sunlit cliffs can undermine themselves as ices within them turn to gas, loosening the matrix of grains that gives the structure strength. A slab slumps, exposing a broad, fresh face that goes active all at once. Compared with a jet, this looks like a billowing curtain, a wide source shedding a cloud rather than a narrow pipe shooting a beam. Brightness rises fast because the active area is large from the start, and it can stay high if the new face remains exposed to sunlight. Rotation can amplify everything. If 3i Atlas is spinning quickly, a jet can be alternately sunlit and shadowed in a single day, modulating the outflow like a heartbeat. If it's slowly tumbling, vents may take turns as the daytime side drifts around, causing a staggered series of surges rather than one continuous blast. The gas itself exerts a tiny push on the nucleus, small but persistent. Over time, that push can tweak the spin, which alters which areas warm, which cracks propagate, and which vents dominate. It's a feedback loop that turns a simple outburst into a choreography. On the observational side, an outburst advertises itself in a few reliable ways. Photometry, the careful measuring of light, catches the sharp rise first, then tracks whether the comet relaxes back to its earlier level or settles into a new normal. The colour of the coma can shift subtly if the dust mix changes. Fresher, smaller grains and different gas contributions tweak the tint. Images might reveal new jets or emphasise old ones that were previously too faint to stand out. In especially clear data, structures expand outward at measurable speeds, like ripples on a pond, allowing estimates of how forceful the eruption was and how quickly it decayed. The environment around the comet shapes the show. If the outburst coincides with a geometry that favours forward scattering, when the sun, the dust and earth line up just right, those newly minted grains become extraordinarily bright from our viewpoint. That optical boost can make a modest mass release look spectacular. Conversely, if the viewing angle is less favourable, even a vigorous event may hide its drama, its light spread thin and its structures washed out. This is why the same comet can seem shy to one observer and audacious to another on the same night. There is always the possibility of fragmentation, literally breaking off a chunk. Small pieces can detach when stresses exceed the material's strength. Thermal cracks link up, a void opens beneath a crust, or centrifugal forces from rotation tug at a weak cape. Fragmentation is a special kind of outburst because it multiplies the sources. The main body and the fresh fragment both shed dust. Their comae can overlap and confuse each other, creating an especially rapid jump in brightness, followed by a more complicated decline. Sometimes the fragment survives, sometimes it crumbles into a trail of crumbs that fade into the general glow. What comes after the fireworks is just as important. The dust cloud keeps expanding, and as it thins, the comet's total light begins to drift back toward its baseline. Gas production eases as the exposed patch cools or becomes mantled again by fallback. Some vents can choke and then unexpectedly clear days later, causing a smaller aftershock. Others stabilize and become part of the comet's regular breathing, active each local afternoon, quiet each night, predictable enough to map. If several regions awaken within a short span, their combined output can mimic one giant outburst, and teasing apart the contributions becomes a detective story. For 3I Atlas, the anatomy is also a biography. The strength of the crust, the mix of ices, the number of old fractures waiting to reconnect, all of that is a record of where it formed and what it endured between the stars. An interstellar traveller might carry a different balance of volatiles than the comets we know, or a surface processed by a harsher cosmic environment. Either way, when it erupts, it briefly turns inside out, letting us read a few pages from a book we didn't write. That's why outbursts are gold. They expose fresh material, amplify signals, and turn a dim, distant speck into a laboratory. And then, almost as suddenly as it began, the show quiets. The coma smooths, the jets soften, the light curve flattens. A new crust settles over the wound. The spring rearms itself, slower this time perhaps, or somewhere else on the surface. The comet keeps going. From a distance it looks as if nothing extraordinary happened, but telescopes remember. Images hold faint shells, spectra preserve hints of different gases, timing records betray a nudge to the spin. Those traces are the autopsy notes of the outburst, the clues that let us piece together its anatomy and, with luck, anticipate the next act. When people talk about optical tricks, they're not saying the sky's faking it. They mean sunlight is doing what sunlight does best, exploiting every chance to bounce, bend and surge in ways our instincts don't predict. With 3I Atlas, the show is all about dust. How much of it there is, how fresh it is, how big the grains are, and how the Sun-Comet-Earth geometry lines up at the moment those grains flood into space. Change any one of those, and the brightness you measure can jump in a way that feels magical even though it's pure physics. Start with the mirrors. A bare comet nucleus is tiny and dark. Think charcoal more than snowball, so by itself it can't reflect much light. But the instant sunlight heats the surface, gas vents begin to loft dust. Countless microscopic grains that act like a cloud of miniature mirrors. Every new grain adds a speck of reflecting area. Multiply that by millions, and the comet's disco ball gets bigger and brighter in a hurry. It's not that the comet turned on a light bulb, it hung more mirrors in the beam. Freshness matters. Dust that has just been liberated tends to be brighter than older dust that's been sun-tanned and coated by residues. If 3I Atlas cracks open a sealed pocket and releases brand new grains, cleaner, icier, less weathered, they'll scatter sunlight more efficiently. Even if the total mass released isn't enormous, a bloom of high reflectivity grains can make the whole coma look dramatically brighter. As those grains age, sublimating, fragmenting, darkening, the boost fades, which is why some comets seem to flash and then settle. Grain size is the second lever. Dust comes in a spectrum of sizes, from smoke-like particles smaller than a wavelength of light to sand-like bits and pellets. The tiny stuff spreads out into a smooth, luminous haze that adds a lot of soft glow. The slightly larger micron to tens of microns grains are efficient forward scatterers. They like to fling light onward in the direction it's already travelling. If a vent suddenly favours that size range, you don't just get more light, you get light steered toward you under the right viewing angles. Big grains help too by contributing textured features, fans and rays, but they're heavier and don't travel as far, so they're less important for the instant wow. Now add geometry, the most underappreciated player. Picture the sun behind the comet from our point of view, with Earth looking almost straight into the dust plume. In that alignment, known as strong forward scattering, the grains act as if they're flashing a headlight right at us. The same amount of dust can appear dramatically brighter, simply because the angles are perfect. Flip the setup, put the sun more to the side or behind us, and the same grains look tamer. Nothing on the comet changed, the spotlight just stopped pointing into our eyes. There's a mirror image effect on the other side of the geometry called the opposition surge, when the sun is almost directly behind us as we look at the comet. Shadows between grains disappear, and some subtle interference effects kick in, making surfaces appear a bit brighter than you'd expect. For comets, forward scattering is usually the big hammer, but opposition can still add a bonus brightening that nudges a noticeable night into a whoa night. Texture and shape of the grains tweak the outcome further. Fluffy, porous clumps, think dust bunnies rather than marbles, present a lot of surface area for their mass. They're extremely good at grabbing sunlight and tossing it around, and they're easily pushed by gas and sunlight, so they can hang in the coma longer and keep the glow inflated. Compact glassy grains behave differently. They can be more directional in how they scatter light but settle faster, or travel on narrower streamlines. If 3i Atlas changes the recipe of what it emits, more fluffy aggregates today, more compact shards tomorrow, the brightness and look of the coma will follow suit even if the total dust output stays similar. Colour tells part of the story without any equations. Many comets look slightly red in visible light because their dust grains carry dark organic coatings that absorb blue light a bit more. When a fresh outburst spits out icier or cleaner grains, the coma can look a touch bluer and brighter. As coatings build up or the ice sublimates away, the tint can drift back toward redder. To the eye, that's subtle. To a camera with filters, it's a clue that the dust population changed, and with it, the scattering behaviour that pumps up the brightness. If you zoom into the inner coma, the tight halo wrapped around the hidden nucleus, you often see structure, jets, fans, and delicate arcs. Those features are not just pretty, they're signposts for where the light is being made most efficiently. A narrow jet aimed slightly sunward and then bent back by sunlight is a powerhouse for forward scattering, because it concentrates the most favourably sized grains along the most favourable directions. As 3i Atlas rotates, that jet sweeps and the bright zones drift, making the total light rise and fall over hours in a way that looks like the comet is breathing. Radiation pressure from sunlight is the silent choreographer that turns chaos into a tale. Small grains feel a stronger push than big ones, so they race outward faster and bend away from the sun more abruptly. This size sorting creates delicate layers, sheets of fine dust farther out that catch and throw light easily, and denser, lumpier material lingering closer in. Right after an outburst, when the inner coma is dense and full of bright, fine grains, the integrated light spikes. A day later, some of that fine dust has drifted outward and thinned, and the brightness ebbs even if gas is still flowing. There's also a neat trick called fragmentation. A grain released from the surface doesn't have to stay a single grain. Sunlight and heat can crack aggregates into smaller pieces, multiplying the total reflecting area without adding mass. Imagine a single mirror shattering into 1,000 tiny mirrors. The surface area you can see jumps. If 3i Atlas liberates fragile clumps that crumble as they travel, the coma can brighten from the inside out as those clumps break apart along the way. From an observer's perspective, it's tempting to attribute every big change to more stuff. But the most honest way to think about brightness is as a product of 3 knobs being turned at once. How much dust is there? How well does it scatter light, and how favourably are we looking at it? A modest bump in all three can equal a dramatic spike in the final number. That's why a surge at 3i Atlas might not look identical a week later. Even if the comet is still outgassing, the geometry knob moved, the grain size knob slid, and the freshness knob faded a little. How do astronomers separate the optical tricks from true activity changes? They normalise the measurements, mathematically peeling away the expected dimming with distance and the expected brightening from geometry to see what's left over. If the corrected light still leaps, that's a strong sign the comet really did ramp up its dust production or switch to brighter grains. If the corrected light stays flat while the raw brightness soared, geometry did a lot of the work. No heavy math is needed in the script. The takeaway is simple. Some brightening is baked into the angles, and some signals the comet itself changed gear. Polarization offers another gentler clue. Sunlight scattered by dust becomes partially polarized. Its waves line up more in one direction. The degree and direction of that polarization shift with grain size, composition and geometry. When a comet's polarization signature changes, it's like hearing a new instrument enter the orchestra. You learn that the dust ensemble has been rearranged even if the total volume brightness stays similar. In practice, a polarization uptick paired with a forward scattering geometry is a tell that small fresh grains have taken the stage. Even the background sky plays a role. A dense coma isn't just bright. It can be optically thick in the very core, hiding fine details and making the centre look smoother than it really is. As it expands and thins, structures sharpen, and the brightness curve softens. Telescopes with different apertures and filters can therefore report slightly different "how bright is it?" answers on the same night, depending on how much of the inner coma they include and how their instruments respond to colour. That's not inconsistency, it's the nature of measuring a living, changing cloud of light. Put all of this together, and the optical tricks behind 3i Atlas's glow up are less mystery than method. A vent opens and injects a wave of bright forward scattering grains. The sun, the comet and Earth arrange themselves so a lot of that scattered light is beamed our way. The grains are fresh and maybe a little fluffy, boosting reflectivity and hanging around long enough to inflate the coma. Radiation pressure sorts them into a luminous veil that keeps flashing sunlight toward us, and rotation keeps the scene dynamic. Then, as grains age and geometry drifts, the surge fades until the next crack, the next batch of mirrors, the next perfect alignment. In short, with comets, brightness is a team sport. Dust supplies the players, sunlight provides the energy, and geometry cues the choreography. When all three line up for 3i Atlas, the result can feel like a magic trick. It isn't. It's the oldest stagecraft in the solar system, and once you know what to look for, you can see the strings. Picture a lumpy, uneven snow and rock body, a few active cracks spitting invisible gas and sparkling dust. Now, let that body spin. Every jet becomes a tiny thruster. That's the essence of how rotation turns a quiet comet into a choreographed performance, and why 3i Atlas can change character in hours. When gas vents burst into sunlight, they don't just brighten the coma, they push on the nucleus itself. The push is small, but it's relentless. Over many rotations, those little shoves add up, nudging the spin rate faster or slower, tilting the spin axis, and sometimes knocking the whole object into a wobble. There are two broad styles of motion to keep in mind. In the tidy version, the comet rotates around one stable axis like a slightly off-kilter top. In the messier version, tumbling, the nucleus can wobble and precess so that no single axis rules for long. Outgassing is a natural agitator. It acts where the vents are, not where a physicist would choose. If most jets sit away from the equator or fire unevenly through the day, They apply torque with a lever arm that's perfect for stirring in some wobble. 3i Atlas doesn't need to spin like a ballerina to make trouble. A gentle, persistent torque in the wrong place is enough to start the dance. Day and night on a comet are short and dramatic. As 3i Atlas turns, sunrise crawls across ridges and pits, flipping switches on the active cracks. Gas ramps up with a delay, there's thermal lag, so peak outgassing often happens not at local noon, but in the afternoon, when the warmed subsurface really starts to breathe. Then dusk slides over, cooling shuts the vents, and the cycle resets. If there are multiple active regions at different latitudes, their on-off rhythms overlay one another like instruments in a band, a long, slow beat from a polar source, a quicker pulse from a mid-latitude vent, and staccato notes from small fractures near the equator. The combined effect shows up in the light we measure, a repeating rise and fall over hours that tells you the rotation period more reliably than any picture. The jets themselves leave signatures you can almost read by eye. A narrow jet that stays sunlit for half a rotation will carve a corkscrew pattern into the expanding dust, like frost smoke trailing from a spinning chimney. A fan-shaped outflow near the equator paints symmetric wings that swing back and forth as the base of the fan rotates. If the nucleus starts to wobble, those patterns drift, arcs thicken into shells, and the spacing between successive features changes. It's like watching a lighthouse beam on a foggy night. If the lighthouse suddenly leans or speeds up, the bright streaks out in the fog shift rhythm instantly. Rotation and jets feed each other. A jet can spin the comet up, which exposes the surface to stresses that open new cracks, which spawn new jets that add more torque. Or a particularly placed vent can break the rotation, damping daytime extremes and letting some areas cool enough to seal back up. Even modest changes matter. A tiny adjustment in spin rate shifts where noon falls on the surface, nudging the subsolar point toward new terrain. After a few days, the afternoon plume you were timing might come earlier, not because the vent changed, but because the clock inside 3i Atlas did. The shape of the nucleus decides which jets get leverage. On a smooth sphere, torque is symmetrical and tends to cancel. Real comets are not spheres. They have lobes, gullies, and cliffs. A vent nestled inside a concavity gets self-heating from sunlight bouncing around the walls. It can stay on longer and pump harder, delivering a steadier push. A jet on a nose or cape sticks out with a long lever arm relative to the mass centre, making it disproportionately effective at twisting the whole body. If a cliff collapses and exposes a broad, fresh patch, that's like swapping a toy thruster for a bigger engine. Rotation notices quickly. Tumbling adds a layer of mischief to the brightness story. When the spin state is clean, the active sources see the sun predictably, so the light curve looks regular. In a wobble, the angles drift from one rotation to the next. A vent that enjoyed 6 hours of sunlight for the past week might suddenly get 8. Another might fall into shadow entirely. To a camera, that looks like unpredictable surges and fades layered on top of the usual rhythm. It's not chaos, it's geometry evolving in real time. Catching and modelling those changes can reveal the nucleus's orientation in space, the location of the vents, and whether the wobble is calming down or getting worse. You can think of the gas as an invisible wind and the dust as confetti that maps the flow. Right after a vent switches on, the gas stream is narrow and strong, scooping up fine grains and flinging them outward. As 3i Atlas rotates, the base of the jet sweeps a curve, and the dust lays down a spiral that expands over hours. Watch carefully on successive nights, and you can measure how far the spiral advanced. That directly tells you how fast the grains are moving, and indirectly how forceful the jet was. If the spacing between spiral arms changes night to night, the rotation period is shifting, an on-the-fly measure of the thruster effect. There's a practical and a poetic side to the spin. Practically, rotation modulates how easily a comet can fragment. If the spin rate creeps toward a critical point, surface material starts to feel light. Slopes that were stable at dawn can become landslides by afternoon. Loose blocks may lift, drift, and resettle, or drift away for good. Even if 3I Atlas never experiences a dramatic break, subtle shedding can flood the coma with bright dust in pulses synchronized to the spin. Poetic or not, that's a very literal way rotation turns into light. From Earth's point of view, rotation also explains some apparent contradictions. You might hear of a quiescent comet that still shows a strong jet, or a bright comet with a weirdly quiet spectrum. If a jet points mostly away from us during the hours you observe, you'll see less dust contribution in your line of sight, even while the comet is working hard. If a vent swings toward us and favours small, forward-scattering grains, you'll get a surge in brightness with only a modest increase in overall mass loss. The same nucleus can be both modest and flamboyant, depending on which face it shows and when. Outgassing doesn't only torque the spin, it nudges the comet's path through space. The integrated thrust over many rotations can shift the trajectory slightly from what gravity alone would dictate. That's one reason orbit solutions improve after a brightening event. There's suddenly enough signal to measure small, consistent deviations, and those deviations encode the spin's preferred thrust directions. If the preferred directions change, say because a new vent wakes up, the orbital fit improves again only after the models catch up. The sky is telling you the comet has replumbed its jets. Seasonality exists even for a visitor on a one-off pass. As 3I Atlas arcs around the Sun, the high-latitude regions take turns leaning into the light. A vent near one pole might dominate before closest approach, then hand off to mid-latitude sources afterward. That seasonal shift can flip the sign of the torque. First spinning up, then spinning down. Stack that on top of any wobble, and you get a rich, evolving beat that lasts for weeks. To observers, it's a reminder that what's the period isn't a single answer, but a timeline. This many hours during the inbound leg, that many after the outburst, a different value again on the outbound path. The surface itself remembers every spin change. Gas picks favourite paths and erodes them into pits and trenches. Fallback dust drifts under the weak gravity and builds insulating drapes on some slopes while leaving others stripped and bright. Over days, those micro-landscapes alter how sunlight pools and where shadows linger, which feeds back into which vents turn on first after dawn. Rotation, in other words, is not just motion, it's a sculptor, carving the very terrain that will decide tomorrow's activity and tomorrow's talks. For people chasing 3I Atlas from night to night, rotation is both problem and gift. It means your measurements can't be taken at random. You want long, continuous runs to trace the full breathing of the light curve. It means images spaced by an hour can reveal moving jets, shifting shells, and spirals you'd miss in a quick snapshot. It also means there's deep information hidden in the wiggles. Match the repeating pattern, watch it drift, and you can infer the length of day, the presence of multiple sources, and the moment the nucleus changed its mind about how fast to turn. And that's the core idea. 3I Atlas doesn't passively bask in sunlight, it navigates it. Every warm noon, every cold night, every crack that sputters to life becomes a tiny manoeuvring burn. Together those burns decide which patches wake up, how much dust is released, when the coma plumps up or thins, and whether the nucleus glides like a steady top or staggers like a tired skater. When you see sudden brightening, weird asymmetries, or a tail that kinks and then straightens, you're reading the logs of a natural attitude control system written across millions of kilometers. Rotation is the metronome behind the music, and jets are the musicians. Listen closely and the whole score of 3i Atlas starts to make sense. When a comet brightens dramatically, everyone asks the same anxious question. Did it just crack, split, or did it ride out a scare and survive? The possibilities range from tiny surface scuffs to a full-on breakup, and they can look similar at first glance. The trick is to read the aftermath. For 3i Atlas, the difference between a recoverable flare and a disaster lives in the shape of the coma, the behaviour of the light over time, and the subtle fingerprints of how dust and gas are leaving the surface. Start with the gentlest outcome, surface shedding. Picture a crust that's been welded together by time and cold, then strained by sunlight and internal pressure until it gives way like thin ice. A vent opens, the comet exhales, and a skin-deep layer of grains and pebbles lifts off. In images, you still see a tight central condensation, the bright, focused core where the hidden nucleus sits, surrounded by a newly plumped halo. The edges of that halo look smooth, with maybe a few fine rays or fans, but nothing lopsided or torn. The light curve, those nightly measurements of brightness, shows a steep rise followed by a graceful slide toward a new normal, not a cliff. If the coma's colour shifts only a little, fresh dust briefly making things look bluer or brighter, and then settles, you're probably witnessing a dramatic venting episode that the comet can shrug off. The surface scabs over. Activity finds a new rhythm. 3i Atlas carries on. A more serious scenario is a crack that reaches deeper than a single vent. Think of a fault line that links several cavities. When it opens, multiple sources switch on together. Now the coma gains texture. Overlapping jets, faint shells, a subtle spiral where rotation sweeps the bases of the plumes. The central condensation is still there, but it looks a touch softer because so much bright dust crowds the line of sight near the core. The rise in brightness is not just big, it's sustained, because the newly exposed ice keeps feeding the outflow. Over days, the light may step down in terraces as sections of the crack choke with fallback dust, pause, and then clear again. It's messy, but survivable. If the rotation period nudges a little, jets acting like thrusters, you've got one more clue that the comet's interior plumbing changed without the body coming apart. Fragmentation is another story. Imagine a slab letting go from a cliff face, or a wedge popping out along a seam. Suddenly there are two sources, even if your camera can't immediately separate them. The coma starts to look asymmetrical, thicker on one side with a faint, elongated brightening that refuses to smooth out. If seeing is excellent or the comet is near enough, careful images show a secondary condensation, a tiny spark just off the main core moving away night by night. In lower resolution, you might notice that the inner coma's brightness profile is flatter than it should be, as if someone set two lanterns behind the same curtain. The light curve often surges higher than a mere outburst would justify, and then decays in an uneven way, fast at first as the fragment sheds its freshest dust, slower later as both pieces settle into separate smaller outputs. Sometimes fragmentation doesn't make a clean twin. The comet may shed a spray of small pieces, pearls on a string hidden in the glow. That can produce unusual tail structure, thin streamers, kinks, and a hazy ribbon that thickens along a preferred direction. The central condensation can fade or stutter as the biggest chunk struggles to keep feeding the coma on its own. If the break is severe, the core loses its sharpness altogether, replaced by a soft, expanding lump of light, a classic sign that the nucleus has crumbled into a swarm of pieces too small to anchor a tight core. In that worst case, brightness may stay elevated briefly. So much new reflecting area, but then it collapses as the fragments rush outward, thin and darken. How do you tell a split from a flamboyant vent if your telescope can't resolve fragile companions? Watch the symmetry. A simple outburst tends to stay centered. The glow grows like a breathing sphere with sunlight pushing a tail straight away from the sun. A split injects directionality. The coma bulges in the direction of the departing piece. Jets that used to trace neat spirals turn lopsided because there are now two rotating sources, each painting its own pattern onto the same canvas. On a good night, you might catch a faint isophote, the outline of equal brightness, pinched into a teardrop rather than rounded. That pinch is a quiet confession that the light has more than one heart. Colour and texture add more clues. Fresh fractures often liberate cleaner, brighter grains, and sometimes a different mix of gases. If filters show the coma became both brighter and a touch bluer, then slowly reddens as ice sublimates away from grain surfaces, you likely saw fresh material exposed. That fits both outbursts and fragments. But if the colour and fine structure change again a few nights later without any obvious trigger, new arcs, a new fan at a slightly different angle, that can be the second voice of a fragment finding its own day-night cycle. Two rhythms overlapping is the hallmark of two bodies learning to breathe separately. Then there's motion. Even a small piece that breaks off leaves a dynamical trail. Multiply the tiny push from jets by 2, and you change the way sunlight's pressure and outgassing nudge the system through space. Astrometric measurements, positions against the star background, begin to drift from a simple gravitational path in a new way. In practice, that shows up as orbit fits that were behaving nicely suddenly needing a tweak, not just to brightness predictions, but to the trajectory itself. If the nudge grows in a direction that matches the asymmetric coma, you're seeing geometry and dynamics sing the same duet. A fragment has gone that way, and both light and motion agree about it. What about the forces that send a comet to the brink in the first place? 3 are the usual suspects. Thermal stress is the quiet saboteur. As 3I Atlas rotates, the skin heats and cools, expands and contracts, linking hairline cracks into highways. Internal pressure is the impatient accomplice. Gases trapped in pores push on every seam, waiting for one to give. Spin is the amplifier. Jets can slowly wind the nucleus up until some patch of loosely bound terrain starts to feel almost weightless, ready to slip. Often it's a mix. Heat primes the crack, pressure widens it, and a whiff of extra spin makes the tipping point arrive a little early. If the surface is layered like a stack of brittle pancakes, failure prefers to run along the layers. If it's more like a welded rubble pile, chunks let go along odd planes, sculpting new capes and coves in minutes. Survival, surprisingly, is common. Comets are fragile, but they're also adaptable. After a scare, fall back dust blankets hotspots, forming a fresh insulating crust. Vents throttle themselves as debris lodges in throats. A rotation tweak moves the subsolar point and eases stress on the wounded area. In images, the central condensation sharpens again, the coma smooths, the tail resumes its plane geometry. The light curve steadies into a slower decline rather than a plunge. That's the comet's version of healing, not a return to exactly what it was, but a shift to a new configuration that can last the rest of its passage. Disintegration, when it comes, announces itself with a string of red flags. The core refuses to sharpen even in steady air. The inner coma grows ragged and diffuse, with no crisp centre to anchor the glow. Brightness bounces in a way that can't be explained by rotation alone. Short, chaotic flickers as different fragments briefly dominate and then fade. The tail may develop odd kinks or a spine, a thin, persistent feature along the path where the pieces are marching. And most telling of all, the overall brightness trend points downhill and keeps going, because there's no longer a single, coherent engine feeding a dense inner coma, just a dissolving cloud spreading thinner every hour. There are pitfalls that can fool the eye. Geometry can make a healthy comet look misshapen. Forward scattering piles extra light on the sunward side, and perspective can stack a normal tail so it looks like a strange spine. Thin clouds, different filters, or apertures that sample different parts of the coma can make one night's measurement look out of step with another's. That's why the verdict, crack, split, or survive, is never made from a single image or a lone number. It's a pattern built from many observers, many nights, many ways of slicing the light. For storytellers and skywatchers alike, the stakes are high because each outcome teaches something distinct. A recoverable flare tells you about the surface, crust strength, volatile pockets, the ease with which fresh ice comes online. A clean split exposes the nucleus's mechanical character, where it's strong, where it's laminated, where seams run. A collapse, sad as it is, turns the comet inside out and floods space with clues about grain sizes, chemistry, and how rubble piles fail. With 3i Atlas, the drama around crack, split, or survive isn't just about whether we get more pretty pictures. It's about whether this interstellar traveller will show us a cross-section of itself, a scar that heals, or a brief, brilliant unravelling. Either way, the light is the evidence, and if you read it carefully, it will tell you exactly how close the comet came to the edge and whether it stepped over. The picture that's emerging is a layered one, built from hundreds of small, careful measurements, rather than a single dramatic frame. Photometry, the nightly measuring of light, shows a clear break in the rhythm, a steep, rapid climb that stands out from the gentle brightening you'd expect just from getting closer to the sun. Observers compare against nearby field stars, check that camera settings and skies were stable, and then stack the results into a light curve. Even after they flatten the data to remove easy culprits like changing distance and viewing angle, the jump remains. It's the signature of real physical change at the comet. After the spike, the light doesn't behave like a popped bubble. It eases into either a slow decline or a high wobbling plateau, suggesting that the surface didn't just burp once. It opened something that stayed at least partly open. In the images themselves, the inner coma tells on the nucleus. Before the surge, 3i Atlas sits as a tight central glow, only slightly more spread out than a star. Right after, the core still looks concentrated, but it's wrapped in a much fatter halo. Stretch the contrast and subtle structure starts to show. Filaments and fans radiating on the sunward side, faint shells expanding out like ripples on a pond, and occasional kinks where a jet bends under sunlight's push. Stack a sequence from the same night and those ripples creep outward at a steady pace. Compare stacks across nights and new layers appear closer in, proving the activity is ongoing rather than a one-and-done puff. Colour is a quiet witness. Using simple filters, many teams note that the coma looks a touch whiter right after the jump, then drifts back toward its earlier tint over the following nights. That's what you'd expect if a lot of fresh, bright grains, some with thin frost, were just released and then weathered quickly under sunlight. The dust continuum, the smooth part of the comet's light, not counting gas emissions, looks a little less red at first, then reddens as surface coatings build and the icier bits vanish. None of this requires tricky math to appreciate. It's the difference between fresh snow thrown into the air and older, dirtier snow left to settle. Spectra add a chemical layer to the story. In the visible, the usual comet bands flicker stronger after the surge, riding on top of the brighter dust glow. In the near-infrared, a warm tail on the spectrum hints at an influx of small grains soaking up sunlight and re-radiating heat, while more volatile-friendly regions of the spectrum show that gas production spiked alongside the dust. The ratios between different bands, dust to gas and gas to gas, don't scream anything exotic. but they do shift enough to say this wasn't purely a geometry trick. The comet changed what it was feeding into space for a while. Polarimetry, the measurement of how scattered sunlight becomes partially lined up by dust, adds a surprisingly sensitive dial. After the outburst, the degree of polarization ticks upward in a way consistent with lots of tiny fresh grains. As the days go by and the coma fills with a broader mix of sizes and ages, that extra polarization relaxes. It's like hearing a flute take a solo and then blend back into the orchestra. The instrument was always there, but for a brief span its voice dominated the sound. If you focus in tight on the inner few thousand kilometers, you can read motion as much as light. The gently repeating wiggle in the brightness, small ups and downs over hours, suggests a rotation period on the order of hours rather than days, and the phase of that wiggle drifts just enough to hint that the spin may have been nudged by the outburst. In some nights of excellent seeing, the base of a jet traces a shallow arc from one frame to the next, as if the nozzle itself is moving with the comet's day. That motion, multiplied across nights, lines up with the photometric wiggle. Rotation is running the show, and the show got louder. Astrometry, the unglamorous art of pinning the comet against the star field, quietly confirms the physical story. Position measurements fit a simple, gravity-only path quite well before the surge. Afterward, models that allow for small outgassing pushes do a bit better. No one is claiming wild deviations, the object isn't firing rockets, but the gentle, consistent nudge implied by the improved fit says, the jets aren't just pretty, they're doing work. Morphology, the shape of the coma, argues against a catastrophic breakup, at least in the immediate aftermath. The central condensation remains crisp, the inner isophotes, contours of equal brightness, are round with only mild pinching sunward, and any asymmetries are modest and explainable by jets plus viewing geometry. On the best nights, there are hints of overlapping fans rather than a second detached core. If a fragment did peel away, it's either tiny, short-lived, or still too close to separate cleanly in ordinary data. The safer reading from the images so far is energetic surface change, not shattered nucleus. One of the more persuasive threads is the way independent groups converge. Small backyard telescopes, mid-size research scopes, and a handful of big facilities all report the same broad timing for the jump, the same pattern of a fast rise and slower evolution, and the same visual motifs: fans, shells, a thicker sunward hemisphere, despite differences in equipment and sky. Even when absolute "how bright is it?" numbers disagree. Because of different apertures and filters, the shape of the curve and the trend in colours line up. That coherence is hard to fake. It's what gives the narrative its spine. If you like single metrics, one commonly used dust proxy leaps alongside the brightness and then decays with a longer tail than the gas indicators. Plainly said, dust production stayed elevated even as the most eager gases began to settle, which fits a surface that's been opened up to sunlight and is still shedding grains efficiently. As the days tick by, that metric steps down in gentle terraces rather than a smooth slope, possibly as vents choke and clear or as rotation favours different patches in turn. Zooming out, the simplest story that fits the data goes like this. 3i Atlas cracked into at least one fresh reservoir of volatiles, switched on a broad outflow of small bright dust, and did so at a geometry that helped beam extra light our way. The coma inflated fast, jets wrote faint spirals and shells onto its face, and the nucleus felt a small torque that tweaked the rhythm of its day. In the following nights, nothing obvious broke off and ran, but the outflow evolved. Grains aged, sizes shifted, and the comet's own rotation moved the spotlight from one patch to another, creating the sense of a living, breathing cloud rather than a static fog. There are still forks in the interpretation. A barely resolved asymmetry in the inner coma could be the signature of a small, short-lived chip. A subtle second periodicity in the light curve could hint at a wobble rather than a clean spin. A deeper look in the infrared might yet reveal a different volatile cocktail than expected for a body this far from the sun. But the weight of the evidence, as of now, leans toward a dramatic outgassing episode and sustained dust release over outright fragmentation. What to watch next is written between the lines of the current data. If the colours drift steadily back and the polarization relaxes, the dominance of fresh, tiny grains is waning. If the light curve's small wiggles shift in phase or amplitude, the nucleus is still being torqued by its own jets. If the inner coma stays crisp and centered, while the overall glow quietly declines, the surface is healing, new crust forming, vents narrowing. If, on the other hand, the core softens, a persistent bulge develops off-center, or a secondary spark appears, that will be the first clean sign that pieces are on their own. For a visitor like 3I Atlas, what the data show so far isn't a verdict, it's a living draft. Each clear night adds a sentence, each filter adds a footnote. The joy is that, even without difficult math, the story is legible. A sudden change on the surface, a flood of bright dust, geometry that helped the glow, and a nucleus that noticed the commotion enough to tweak its own spin. From here, the plot will either settle into a quiet epilogue or wind up for another twist. Either way, the evidence is already rich, and it's pointing to a comet that's more active, more dynamic, and more talkative than the cautious forecast dared to expect. Before you can understand why 3I Atlas feels so shocking, you have to remember the two trailblazers that set our expectations. The first was Oumuamua, a dim needle-in-a-haystack visitor that broke every casual rule of comet watching. It never grew a photogenic coma, never unfurled a bright tail, and yet it didn't move exactly as gravity alone said it should. Subtle hints of extra push, without the usual gas and dust fireworks. Its light flickered in a way that suggested a weird shape and a complex spin, maybe even a gentle tumble. It was aloof, almost stingy with clues, forcing everyone to argue about what could power a nudge without leaving obvious fingerprints. The second was Borisov, the anti-Oumuamua in spirit, unmistakably cometary, with a classic fuzz, a clear tail, plenty of small dust, and chemistry that looked comfortingly familiar. It brightened and behaved in line with the comets we've known for decades, just faster and colder because of its interstellar pedigree. Between those two, our mental map had two pins: quiet, puzzling drifter, and textbook icy traveller. 3I Atlas lands like a third pin that redraws the map. It isn't the silent, almost airless pebble Oumuamua seemed to be, and it isn't a by-the-book performer like Borisov either. It's a talker, capable of a sudden surge that yanks attention from the entire observing community. That abrupt jump in brightness, the suddenly 16 times brighter moment, tells you this visitor has both the means and the willingness to rearrange its face under sunlight. That alone makes it different. Where Oumuamua whispered and Borisov conversed politely, 3I Atlas occasionally shouts. Line up their light curves in your mind. Oumuamua's was spiky on short timescales because the object itself rotated and presented different faces, but its overall brightness never made a comet's grand entrance. Borisov climbed and faded along a gentle, predictable arc. Steady outgassing, steady dust. The kind of curve you could plan a week around. 3I Atlas drew a neat line and then broke the pencil. An unmistakable step upward. The mark of either a vent switching on, a crust yielding, or a geometry that suddenly favoured forward scattering of fresh dust. That break in rhythm is the kind of thing you associate with temperamental solar system comets, not with an interstellar veteran that's supposed to be desiccated and calm. It puts 3I Atlas in a previously empty part of the interstellar plot, active but not merely steady, dramatic but not necessarily falling apart, considered dust. Oumuamua frustrated everyone because it seemed to carry little or none in the way we could easily see. If dust was there, it stayed close, fine, or sparse enough to keep the coma invisible. Borisov, by contrast, was a dust factory, tossing out small reflective grains that made it look like a familiar long-period comet. 3I Atlas leans closer to Borisov in that it can clearly flood space with dust, but the character is different. It's capable of a big, fresh wave of grains in a short time, and the brightness leap suggests those grains were either small, clean, or aligned in a way that channeled light toward us. That's not just more dust, it's different dust at a decisive moment. The lesson is that interstellar comets don't merely range from dusty to dust poor. They can change dust modes on the fly. Now think about gas and the mechanisms that lift that dust. We never caught Oumuamua spraying an obvious cocktail of gases. The arguments about what propelled it moved through exotic possibilities because the usual suspects were so hard to see. Borisov reassured us. Ordinary volatiles could explain most of what we saw, and it fit into the familiar framework of ices waking up as sunlight worked through a porous crust. 3I Atlas feels like a controlled experiment midway between them. It clearly had the capacity to loft dust rapidly, which implies energetic gas flow, but it hasn't, so far, broadcast the kind of showy, continuous venting that would make its entire apparition predictable. Instead, it behaves like a surface with pockets and gates. Quiet, quiet, then open the valve. That toggling hints at a crust that's patchy in strength, with reservoirs waiting for cracks to connect them to daylight. Spin and stability draw another contrast. Oumuamua's changing brightness suggested an odd shape, or a ragged tumble. An attitude problem that made it hard to treat like a simple spinning top. Borisov looked more like a steady rotator with activity that didn't kick it into strange motions. 3I Atlas shows the fingerprints of jets acting as thrusters, small, repeating wiggles in brightness that look like a rotation signature, with hints that the period may have shifted around the outburst. That places it squarely in the camp of jets and spin talk to each other, a behaviour solar system comet observers know well. It also means the same object can look subdued one night and lively the next simply because a different patch rolls into the sun and takes its turn. From a structural point of view, each visitor probed a different weakness. Oumuamua felt like the extreme end of space-weathered, surfaces processed by radiation into something tight and dry, enough to resist the usual kind of cometary breathing. Borisov felt canonical, a nucleus that reacted to heat by venting, fragmenting a bit near its closest approach, and leaving a familiar dust trail behind. 3I Atlas looks laminated, parts that are ready to open, parts that are stubborn, a skin that can hold until some threshold is crossed, and then give way broadly enough to change the whole appearance. That threshold behaviour might be the most important addition to the interstellar playbook. These travellers can act stable until they aren't, and when they tip they can mimic either a classic comet outburst or the early phases of a split. The three together widen our sense of where they were born. Borisov's chemistry and dust looked like it came from a cold pantry beyond the snow lines of its home system, the kind of place where carbon monoxide and other eager ices are common. Oumuamua hinted at either unusual composition or unusual processing. Perhaps ices baked and reworked into something tight and odd over a long, lonely voyage. 3I Atlas argues that even if interstellar comets start with broadly similar ingredients, the packaging matters: porosity, layering, grain size, and crust strength. Two comets can be stocked with similar volatiles and still behave differently if one is riddled with sealed pockets and the other is more evenly ventilated. Observationally, each changed how we watch the sky. Oumuamua proved we could find something tiny and nearly featureless, and still learn from its subtle motions, which push survey teams to refine how they flag almost invisible movers. Borisov proved that when a true interstellar comet acts like a regular one, our standard toolset works beautifully. Photometry, spectra, polarimetry, the whole orchestra, and the global network can coordinate quickly. 3i Atlas adds urgency and flexibility. It tells schedulers to leave room for surprise, because a visitor can reclassify itself overnight. It also validates the role of amateurs and mid-size observatories that can sprint. When the brightness pops, those teams are often the first to catch the new jets, the fresh shells, the short-term colour changes. There's a cultural lesson too in how theories get tested. With only Oumuamua on the books, the temptation was to generalise from a single strange data point. With Borisov, the temptation flipped. Maybe most interstellar visitors are just like our comets. 3i Atlas kills both temptations kindly. It sees the category is broad. Some will be austere, some exuberant, some unpredictable in bursts. It pushes us away from one-size-fits-all stories toward a small-body zoo where you expect variations in texture, timing, and temperament. That's good science. It trades neat narratives for better, messier truth. Even the public-facing drama differs in a way that helps. Oumuamua's mystery lived in absence. No tale, no obvious venting, only inferences, which made it ripe for speculation far beyond the data. Borisov's beauty lived in presence. Bright coma, clean tail, classic behaviour, which made it a perfect ambassador for interstellar but familiar. 3i Atlas lives in change. It teaches viewers to look for evolution, a coma that fattens, shells that move, light curves that step, texture that reorganises. It invites people to follow along night after night, not just to marvel at a single postcard image. Where does that leave the big questions? What these visitors are made of, how they're launched from their home systems, and how common each type might be. Across the trio, a pattern emerges. Ejection is probably promiscuous. Planets fling out icy rubble of many kinds, from dense, crusted shards to fluffy, volatile, rich snowballs. The long haul between stars doesn't impose a single fate. It can harden some, preserve others, and set up threshold behaviours in many. When such bodies finally cross our sunlight, the response ranges from quiet radiation pressure nudges to full-throated outbursts. 3i Atlas strengthens that middle ground. Interstellar comets can carry enough accessible material to put on a show, but in punctuated acts rather than a steady performance. In practical terms, that means future strategy should borrow a page from this encounter. When the next interstellar spec is flagged, the plan shouldn't be either Oumuamua-like or Borisov-like. It should assume a moving target. Start with high-cadence photometry to catch steps and wiggles, sprinkle in colour work to watch grain populations change, and be ready with fast-trigger imaging that can map jets before they fade. Keep a close eye on geometry, because forward scattering can masquerade as physics, and revisit often enough to catch thresholds when they tip. And perhaps the most generous lesson is about humility. 2 visitors were enough to create a story template. 3 broke it in the best possible way. 3i Atlas reminds us that nature's sample size is bigger than ours, and that the solar system is a stage where guests from different neighbourhoods will behave in ways that reflect both their origins and their journeys. Oumuamua gave us silence with a wink, Borisov gave us a familiar song, and 3i Atlas gives us a drumbeat, quiet, quiet, boom. With each new act, we move from guessing to recognising patterns. The category interstellar small bodies is no longer a curiosity, it's a field. And thanks to this sudden brightening, That field now includes thresholds, texture, and timing as first-class characters in the story. So what happens next is a mix of physics, patience, and a little stagecraft from sunlight. After the jump in brightness, 3i Atlas won't simply flip back to quiet mode. Freshly open terrain doesn't seal overnight. Expect a phase where the comet breathes. Modest rises and dips over hours as rotation swings active patches into and out of daylight, layered on top of a slower trend that will either settle toward a high plateau or taper off. If the new vents remain exposed, dust outflow should stay elevated for days to weeks, with the coma looking fuller and more structured than before. If fallback dust blankets the area, production will ease, and you'll see the inner glow contract and smooth out. Either way, the first thing to watch is rhythm. Does the light curve repeat with a steady beat, or is it drifting as jets subtly torque the spin? Geometry will likely play a louder role in the coming weeks. As the Sun-Comet-Earth angle changes, some nights will supercharge the view. When that angle shrinks, forward scattering can beam sunlight through fresh dust straight toward us, making 3i Atlas look extra vivid even if activity hasn't changed. On those nights, the sunward side of the coma will seem especially swollen and the tail more sharply etched. As the angle widens again, the same dust will look more subdued. That isn't the comet losing steam, it's the spotlight moving. Mark the bright bonus nights. Comparing them with more neutral angles later will help separate real physical changes from optical boosts. There is a non-zero chance of aftershocks. Once one crack opens, nearby seams are under new stress. A minor outburst, smaller than the headline event but still obvious in side-by-side images, wouldn't be surprising. These tend to happen when a rotating vent clears itself, when a thin crust on an adjacent patch gives way, or when afternoon warmth reaches a pocket that morning light couldn't. Watch for subtle arcs or shells expanding from the core over a few hours. Those ripples are timestamps, letting you measure how fast the dust is flowing and whether a second pulse just joined the party. Fragmentation is the wild card everyone wonders about, and the odds rise if rotation continues to change. Most splits start small. A chip peels off, too close to separate at first, but it tugs the coma off-center and flattens the brightness profile near the core. If that happens, the inner light won't sharpen cleanly even in steady air, and the brighter side of the coma will persist in the same direction night after night. If a secondary condensation appears and inches away, you'll know the story. More likely though, 3i Atlas survives the stress and reskins its wound. Comets are fragile, but they're good at quick, messy repairs. For professional teams, the next steps are almost scripted. High-cadence photometry will pin down any change in the rotation period. Was the nucleus spun up by its own jets, or did it break a little? Colour monitoring will check how the dust population evolves. Fresh, bright grains make the coma look slightly whiter, then drift back toward warmer tones as frost burns away and residues build. Polarimetry, if available, will keep an eye on the fraction of tiny grains. A gradual relaxation from a post-outburst peak would fit a coma, maturing from brand new glitter to mixed confetti. Spectroscopy will try to catch the relative rise and fall of the usual gas bands. Some species spike fast and fade fast, others linger, while mid-infrared work, where possible, will weigh the warm dust directly. Radio and millimeter dishes may listen for the coldest molecules, the slow, steady drumbeat beneath the optical show. If you're following along from a backyard or a small observatory, you can contribute more than you think. Log brightness with consistent methods. Same exposure time, same aperture for measuring the inner glow, same comparison stars. Stacking short exposures works wonders. Keep stars round, track the sky, not the comet for photometry, and stack on the comet for pretty structure shots. Try a simple filter sequence. clear/luminance for dust, a blue or green filter to accent the sunward fan, and, if you have one, a narrowband comet filter to tease out gas. Note the time precisely. The rotation-linked wiggle is on the scale of hours, and your measurements fill gaps the big telescopes can't. Sketches are underrated. If you note where the jets and fans tilt from night to night, you're recording geometry in a way numbers alone can miss. For imagers hunting structure, aim for long, calm sequences rather than a single deep shot. Jets move. Shells expand. A 90-minute run lets you watch the inner coma evolve in real time. Gently stretch your data and experiment with contrast masks to reveal faint arcs without inventing them. Compare your results with the previous night at the same local time to see if a feature is rotating, fading, or truly new. If the inner core stays tight while the outer halo swells, the vent is steady. If the core looks flat and the halo is lopsided, consider fragmentation or overlapping fans. Share your frames and numbers with community databases. Coherent coverage across longitudes is how the story sharpens. Safety notes matter, even for veterans. If the comet sinks near the sun in the evening or dawn sky, resist the urge to chase it too low. A few extra degrees of altitude beat a risky horizon shot every time, and there will be better windows as geometry improves. If it passes near bright stars or through the Milky Way, expect the brightness estimates to bounce. Background confusion isn't a comet problem, it's a sky problem, and repeating the observation an hour later often clears it up. Expect the outbound leg to be slower and moodier than the inbound. Heat seeps inward as 3i Atlas rounds the sun, and that stored warmth can keep pockets simmering long after the closest approach. That's why some comets look deceptively healthy as they depart. Activity is being fed by yesterday's sunshine. Over weeks, the coma will thin and the dust will sort by size. Fine grains drift away, larger ones hang closer in and contribute more texture than glow. If the comet had a big outburst, a subtle dust trail can form along its path. Deep, wide-field images in a dark sky might pick up that ghost long after the main show dims. From a storytelling perspective, there are 3 endings to watch for. In the quiet ending, 3i Atlas tapers gracefully, the light curve smooths, the inner glow sharpens, and the jets turn from fans to wisps. That's a healed surface and a successful passage. In the complicated ending, small aftershocks dot the outbound months. A minor surge here, a new arc there, as different seams take their turn. That ending is rich with clues about crust strength and layering. In the dramatic ending, evidence of a split appears. The core softens, a secondary spark emerges. The inner coma bulges in one direction for days, and the comet becomes a duet. Each path teaches something different. None of them is failure. If you want a simple checklist for what to log, make it this: brightness at consistent settings, coma diameter in arc minutes, or the size of the inner bright part through your usual aperture. A short note on shape: round, fan sunward, arcs visible, lopsided, secondary point, and any colour impression relative to nearby stars if you're observing visually. Repeat that every clear night you can. If a change jumps out, an extra shell, a new direction to the fan, an unusual fade, flag it promptly so others can confirm. Science loves surprises, but it loves confirmation even more. Finally, keep your expectations flexible. The most honest forecast is that 3i Atlas will keep evolving, sometimes for reasons you can see, new dust, new jet, sometimes because the angles favoured or punished the view. The delight of this visitor is change, a living light curve, a coma that reorganises, structure that drifts with a comet's day. If nothing explosive happens, you'll still watch a rare interstellar traveller write its weather across the sky in slow motion, And if something does, another surge, a small fragment, a lingering trail, you'll have the context to understand why it matters. Either way, the way to follow is clear. Look often, look carefully, write it down, and let the pattern emerge. 3i Atlas has already taught us to expect thresholds. Now we get to see whether it settles into a calm epilogue or saves one more twist for the road.